Alright, silly people, here's the situation. We're given a fancy U, which I can only describe as a potential, that we're supposed to plug into the covariant form of a Lagrangian, and then apply the covariant form of the Euler-Lagrange equation to it, and get an equation of motion. Um, so first thing I want to do is I want to just go ahead and finish writing out what the Lagrangian is. It's going to be m over 2 u nu plus a lambda nu. It's a function of x mu, and that's kind of a dummy variable that you can um, assume any form of. It's a function of position um, times u lambda u nu, right? So taking the partial derivative of that with respect to u nu. Goldstein is kind of fast and loose with his partial derivatives. I'm going to try and be as explicit as I can for this guy. So it's going to be m over 2. You have a product rule. You're doing u sub nu del u super nu del super nu, right? Plus u super nu del u sub nu del u super nu. And then a lambda nu isn't a function of velocity, but so you have u lambda del u nu del u nu, and then u nu del u lambda del u nu. Okay. So whenever you take partial derivatives of four vectors like that, you're going to end up with delta functions where you have subscripts and superscripts that are the same given in the derivative. So it's looking like u nu, and then you have a Kronecker delta with two nu's up top, and then you have u super nu, Kronecker delta, one nu on the bottom, one nu on top. And then you got this guy. You have u lambda del super nu plus u super nu del super nu super lambda. All right. Whenever you have a Kronecker delta where both of the superscripts match, it's just equal to 1. Whenever you have one which has a subscript and a superscript, it actually raises or lowers whatever it's attached to. That's one, and then this one will change the superscript on whatever is attached to the thing that doesn't match, so it's lambda. So we're writing this as m over 2 u nu plus u nu plus a lambda nu. Then you got u lambda plus u lambda. Lovely. Then just combine like terms. You got m times just one factor of u sub nu, and then plus 2 a lambda nu u lambda. All right. Now we got to take a time derivative of that. So d tau del lambda del u nu. You have d tau of m u nu, and then 2d. You got a u lambda d lambda nu d tau, and a 2a lambda nu du lambda d tau. All right. Mu nu is actually the definition of the world momentum. So I'm going to write it like that. So it's going to be dp sub nu d tau, and then taking the time derivative of the tensor a lambda nu. It's not a function of time explicitly, it's a function of position, which means we can take a partial derivative of it with respect to position, then multiply it by d position d tau. So I'm talking about u lambda dx nu d tau times partial a lambda nu partial x nu. And then the other term stays the same. Right. And then, by definition, the time derivative on world momentum becomes a Minkowski force. So that's k sub nu. But nothing else really. Oh, yeah. So, and then dx nu d tau is just u nu again. So we're doing plus 2 u lambda u nu del a lambda nu del x nu. Put that kind of in a gross way. There it is. Plus 2a lambda nu du lambda d tau. All right. Now let's do the other derivative that we have to do. We have to do del. We have to take the partial of the Lagrangian with respect to position now. The only thing which depended on position was the tensor a lambda nu. So you just have u lambda u nu del a lambda nu del x nu. It's supposed to be del x nu. So it's identical to this term. So we get a little bit of nice cancellation. So now rewriting all of that, you have k nu. So we're doing the Euler-Lagrange equation now. K nu plus u lambda u nu del a lambda nu del x nu. And then we still have this thing. Is 0. And then the problem does ask you to solve for the components of the Minkowski force. I am going to solve for all this stuff then, so it's going to be k nu is equal to minus u lambda u nu del a lambda nu del x nu plus or minus 2a lambda nu du lambda d tau is, yeah, that's it. So the zeroth component of the Minkowski force then, u lambda u0 del a lambda 0 del x0 minus 2a lambda 0 du lambda d tau. The only thing that you can do to simplify this is x, the zeroth component of x is just ct, and then u0 is just gamma c. So you're talking about doing minus gamma c u lambda del a lambda 0 del ct. You still have to sum over lambda, so I think this is the simplest it gets without knowing what lambda is, or without knowing what a is, I guess. Then the first, second, and third component of the Minkowski force um, will look like this. So it's u lambda ui del x lambda I del xi minus 2a lambda I du lambda d tau, where ui is now just a velocity component, and then all of the xi's are position components. So not too different there. Okay.